Our final presentation is Nexus Aurora. Do we have everybody in the panelists for this?
I believe we do.
Awesome.
Save the best till last.
Go ahead, Nora. Start the clock, and you guys can go.
Hello. Speaking to you from South Africa, the United States, England, Canada, South Korea, the Netherlands, and with the support of our team from all around the world, we are Nexus Aurora. When this community was founded as an open source project about 6 months ago, we could have hardly imagined we'd be here today, and we thank you for that privilege. We're an oddity at this convention. We don't represent some established organization. Our members aren't from an institution with a history of space exploration. We come from a diversity of countries, backgrounds, ages, educations, experiences. All we share is a passion for pushing frontiers, and yet we very sincerely hope, brought something new to the table. A fresh perspective, a holistic approach, buzzwords, but the very firm belief that colonizing, not exploring, but colonizing Mars for good, requires a radical departure from traditional thinking. In order to even begin planning for a realistic, achievable city, we had to re-examine an awful lot of assumptions about living on Mars. For the past 6 months, we've iterated over these ideas, argued, researched, resynthesized. And what we present today is a product of that synthesis. It's very unlike many other proposals explored. Ours is a city of water designed to bleed heat and oxygen into the sky, a delicate assembly of automated labor and human endeavor on the slopes of Hellas Planitia, a society built around architecture and an architecture built around society. Our city has the nature and the challenge of Mars baked into its design. As we reshape the planet to fit ourselves, it reshapes us to better adapt to it. This presentation may be different to many you see today because it will not focus heavily on our technical work. For that, we have our 20-page report and we have our Q&A. Instead, we want to talk about our decision-making, our unlearning, our relearning of the challenges of Mars. We'd like to invite you to step through the looking glass and look at old problems with new eyes.
Historic works on the government of Mars, both fictional works and non-fictional studies, have been focused on applying an already known form of government to the Martian state. However, we have come to the conclusion that the political environment of Mars is drastically different from the one on Earth. This means that a new form of comprehensive government to allow the maximum flexibility for the population, while providing checks and balances to prevent destabilization is required. The Martian government is built on the principle of communitarianism, long-run sustainability, and most importantly, the room for amendment. The government system of Nexus Aurora recognizes that the progress and changes of the system is an essential part of the representative government. De jure involvement of the law reinforcement in the judicial branch and the addition of a new anti-corruption branch to the 3 divisions of government to make sure that the government can react to both internal and external changes quicker than the conventional government. As the core agenda of building the Nexus Aurora truly independent, the economics of the project had to research and adopt experimental and medical solutions, one of which was to acknowledge 2 facts which are easily overlooked by other groups. First one being that the Nexus Aurora will not be the only Martian settlement, and the second one being that the economic independence of Mars City does not mean that it will not have foreign earthly influence from both the governments and corporations. The 9-month journey between Earth and Mars means that the tertiary sector businesses, including B2C service and tourism, will not be sustainable due to the extremely small scale of businesses. Thus, Nexus Aurora aims to become an organic and central part of the Earth-Mars connections, becoming the distinguished port and factory city of the planet. Nexus Aurora will be exporting the resources required to construct settlements to nations, aiming to become the viable alternative to transporting the required resources from Earth. Nexus Aurora aims to pay back the state debt accumulated from the initial stage of the city founding in the frame of decades, and even centuries, via the economic strategy of currency devaluation, as shown in the graph below. Nexus Aurora realistically recognizes that corporations will not be investing in the Martian city-state just because of the wow factor. The Mars colony will be providing fundamental analytic qualitative investment opportunities for the corporations. The government will be in charge of the import and the export of perhaps the most costly civilian cargo transportation. Thus, the contract with the Mars government will serve as the most extensive seal of quality in history and function as the verification of management and corporate governance. Concern regarding the excessive involvement of corporations and the entanglement of the investment and political influence is real and threatening. To solve this problem, all investment to Mars will be qualified and quantified in the form of national bonds, ensuring political liberty and investment payback. To keep the influence of a single corporation in check and minimize the investment risk, a format of government-led consortiums will be used.
The traditional doctrine of landing zone selection is choosing the northern hemisphere for the short winters, going as close to the equator as possible for the solar power, and finding a flat area. This is great for a short-term outpost, but doesn't work for a long-term settlement. For a million-person Mars colony, in situ resources are much more important. We need to land kilometers from thousands or even millions of tons of relatively pure water ice, which for us meant glaciers. This restricted landing zones to places about 30 degrees north or south of the equator. Minerals are key. If we want to have a successful colony, we need to have some path to becoming less reliant on Earth imports, which means mining on Mars. For our purposes, the best indication of where useful minerals might be located in meaningful quantities is fluvial activity, which is ancient riverbeds. So we chose Hellas Planatia. Why Hellas? Well, it's packed with glaciers, with billions of tons of water ice nearby. Glaciers are important because it means that we will not have to rely entirely on extracting water from the soil. Melting glaciers is something that humans are very good at here on Earth, so we plan on bringing those skills with us to Mars. The very low elevation in Hellas means that we have almost twice as much atmosphere from aerobaking and protection from radiation as you would have at topographic datum. Low elevation also means that water may be able to flow in liquid form on the surface during some seasons. Our landing site is about 5 kilometers from the western bank of Dow Vallis, which provides a wealth of opportunities for prospecting. Tilling the soil in search of precious minerals provides a low-tech and simple solution for our early colony needs. Here is a 3D projection of what our landing site looks like. Our site has large open spaces for building, glaciers for fresh water, and craters for the safe launch and landing of spacecraft. Nexus Aurora is very community-driven, so all of these names were crowdsourced. Part of the reason why going to Mars is such a great idea is the science that we can perform on the surface of Mars. In West Hellas, there's a point 9 kilometers below Martian datum, the lowest elevation point on Mars. At this point, the pressure is so high that liquid water is hypothesized to be able to flow on the surface during large parts of the year. It is a prime location for potential astrobiology research, and the best way to conduct science is with humans on the ground. Outposts will be created hundreds or even thousands of kilometers from our main base and can be occupied by somewhere between a few dozen to a few hundred people and can be seasonal. Mining outposts are planned at geologically interesting sites to look for valuable minerals, and a northern outpost is planned for farming. Going 1,000 kilometers north almost doubles the amount of solar radiation, so it is worth creating a farming outpost to supplement the farms in the city center.
The city's bootstrapping process is critical to understanding the materials and architecture we have chosen. Everything in the city is limited by what the Martian industrial complex can provide, and we'll need to prioritize based on material cost. Unless we have a solid understanding of this evolution of resource scarcity and value, it's impossible to design a realistic, practical, low-cost city. You import as much as you can, but every person in the city will need several tons of materials, buildings, appliances, tools, vehicles. So ISRU needs to begin immediately, starting with water and expanding the variety of products that we can make from basalt. Even during the first synod, we're going to need to move regolith off the glaciers. To get to the water, we need to make hydrogen, to make methane to refill the starships so people can get back to Earth without a trampoline. We'll mine extra water for drinking and radiation shielding. If you compress regolith, you get Mars bricks to build solid radiation-resistant walls and roofs. Leaching can extract common metals like iron, aluminum, and magnesium. For steel, we can perform direct reduction with hydrogen and then roll into sheet metal and structural members like I-beams. Basalt can be melted, even with concentrated solar, to spin basalt fibers for insulation and structural tensile members that can be laminated into pressure vessels. We've tried this, and they hold 1 bar easily. That's a picture of our prototype on the right. If you wash out the perchlorates and add nutrients, you can make soil to grow food.
Civil engineering also needs concrete, but without sufficient limestone on Mars, we chose to use polymer-based concrete. We have done some promising experiments using Fischer-Tropsch wax as the polymer to bind basalt dust and fibers together into fully ISRU composite materials. By contrast, thermoset plastics or chemically curing concrete eventually become a resource sink because they are hard to repair or recycle. Embodied energy needs to account for full life cycle costs. Mars does not have oil, but short, straight carbon chains like waxes and polyethylenes can be made via Fischer-Tropsch synthesis from CO2 and hydrogen, exactly like Saboteur methane. But cyclic organics aren't easy or cheap to make directly from gas, and industry needs a wide variety of them. So we've chosen flash pyrolysis and hydrothermal liquefaction of fermented cellulose waste and algae as our feedstock, creating a rich product full of benzene, naphthene, xylene, and dozens of other volatile aromatics and polycyclics, which are essential feedstock or starting compounds for industrial materials. We also get a tar that can be mixed with perchlorate salts to make explosives for blasting hard rock. We've tried this, and we get a carbon char that can be used for absorbing atmospheric contaminants or as a soil amendment. We do not have the excess materials or energy to waste either one in landfills, so everything must be recycled.
On Mars, humans are our most valuable asset, so we must not waste human effort on tasks that can be easily automated. As such, the city itself is designed from the ground up to include robotics and automation in its design. Elements include the environmental and structural sensors, automatic routing of vehicles, and an entire sublevel of the city dedicated to the rapid movement of cargo robots. The industrial system of the city will be heavily automated, with robots working in mining and construction, as well as automated production facilities. Robotics and automation will be ubiquitous in Martian life. In order to maximize the efficiencies of these robotic systems, most of these robots will be on a mobile base on which different modules will be mounted, with more specialized robots only taking shape when it is more cost-effective than bolting on a module to a generalized base. These bases can even be networked with each other and with external sensors in order to move massive objects. The need for this efficiency even manifests itself in the logistics system in the form of standardized containers made of sheet metal at the domestic scale, effectively replacing the cardboard box and laundry hamper, as well as larger containers for the mass transport of goods. All of these containers are capable of nesting together and are individually tracked using an internal UICC chip, aka a SIM card, as a sort of rewritable barcode. Each container is designed to be transported by autonomous systems, effectively handling 100% of cargo and strap transport automatically. However, we did not stop there. The Technosphere concept arose from the need to maximize city-wide resource efficiency and coordinate between the various robotic and human elements of the city. It is effectively an autonomous planetary IoT network that can make decisions without human intervention, using data from a distributed city information model database. Tracking the millions of sensors embedded in all systems across the city, the system then redirects resources, traffic, personnel, production, and robots automatically as the need arises. This control even extends to the biosphere, allowing the ever-flowing web of information to move air, heat, and water to where they are needed most. It is no longer the smart home. The Technosphere is a self-sustaining smart planet. Understanding the growth of industry isn't just an engineering exercise. It informs the decision-making about everything else within the city, as each design decision has secondary impacts on the entire industrial ecosystem. Material availability and full life cycle costs are what set the fundamental constraints for the design of our city.
Once the mining industry is operational, it becomes much easier to transition from temporary habitats, like the temporary 6-meter models currently shown, to more durable habitats. This means that the growth fueled by our industrial capabilities will impact urban growth. From settlements, we go to a city. More industrial capabilities means a bigger population, and as such, more complex habitat. There are many challenges to overcome, of course, before we can achieve a sustainable city on Mars. According to our projections, it is estimated that while the population will be multi-generational, most of it will be coming from Earth. In our report, we state that 95% of the city's population will be Earth-born and will be very culturally diverse. People will most likely speak many languages in the city, which complexify things like emergency procedures and civil conduct. We have to make sure these people can get along to brave this hostile planet and make it their home, to give us the best odds of social cohesion, but also to make it an attractive place for families, workers, and investors. We thought it was important in our designs to provide natural sunlight, shading from radiation, and space for cultural expression through an interconnected city. We can achieve this on the surface of Mars by using the craters to our advantage. Our main industrial and interplanetary activities are located inside craters because they offer natural blast protection, for example. We also identified 19 sites with craters averaging a diameter between 200 and 350 meters. They are located in the area surrounding our landing sites and the glaciers in Dow Valleys, where we plan to have a nuclear reactor as a source of power. And they are also near Game Crater on the top of the right picture, where our main industrial and mining facilities are located. We imagine that by casting a transparent dome over these smaller craters, we can achieve a design that offers a big open space with natural sunlight and shielding from the Martian environment. All of these craters become interconnected by a network of electric rails and roads with a high rate of automation thanks to the Technosphere. So they become the centerpiece of a neighborhood. We think craters have a real potential of being culturally impactful landscape features, especially if they are to be shared by a very diverse community. And areas next to these craters can be leveraged for real estate value. To make them as attractive as possible, we decided to design them as gardens. And as such, we followed the principles of city growth developed by Ebenezer Howard more than 100 years ago. On the right image is an example of this application. The blue dots represent these gardens. Everywhere these domes are deployed, they signal the transition from temporary settlements to more durable habitat. Each garden can be designed based on the main functions it serves, be it scientific, industrial, residential, economic, or even institutional, and facilitate cultural expression, collaboration, and self-sufficiency. Along with these gardens, nodes consisting of craters and their surrounding areas become poles of human activity in order to create a neighborhood. In due time, and with the city growing, those neighborhoods might eventually sprawl toward one another, making it a full-grown, interconnected, and sustainable city garden.
The architecture has been selected first and foremost to serve people. People must want to live on Mars. They don't have to live on Mars. And the construction used to build the city has a massive influence in this. Even in the harsh Martian environment, we discovered that there's not one answer to buildings on Mars. Only certain constraints due to the new environment. Considerations such as material availability, pressure, radiation, and temperature has informed all of our design choices. With the aim to create large open spaces for communities to gather and do human things, we designed our domes. Pressurized domes do not want flat bottoms, so we place them in craters with a natural bowl shape. These are actually just large spheres, but you only see the top. The communal spaces are well below ground level, and even though exposed to the open sky, should have radiation exposure below that of the open surface. A few hours a day here should be fine. Temperature fluctuations are a concern that we solve by using active coatings that become reflective with a small electric current. This allows us to reflect heat back into our structures, keeping them warm during the night. For our main building type, we aim to create large, well-lit spaces that allow people the freedom to do almost anything they want inside. These structures also need to be safe from radiation, pressures, and temperatures, all while being fairly cheap to build. To do this, we fuse a series of cylinders together, held in place with tension rods, similar to how an air mattress works. For radiation protection, we build thick regolith walls to create a dam for melted glacial water overhead. This should reduce daily radiation to safe levels. We can now insert windows through the walls to allow for views to the new frontier. The ceiling is made from a clear membrane, allowing light to filter through the water into the structure below. Even under all this water on Mars, the light inside the structure will still be many times higher than your typical well-lit office, allowing for plants to grow without any supplementary lighting. A thin membrane overhead preserves the water at a lower pressure, which can allow us to use this water for a range of other activities. Anything from assisting the cooling of nuclear reactors to fish farming, and even water skiing becomes possible on Mars. Natural greenery, along with good amount of light, is essential for healthy human development. We really want people to be able to explore our city and walk from one corner of it to the next, and never really feel trapped inside dark, lonely corridors. So we designed large passages with roads up to 12 meters wide where pedestrians, cyclists, and slow-moving vehicles can travel between nodes, habitats, and train stations. These areas are big enough for small stores and workshops, keeping the road fronts busy and exciting. Also, having water overhead allows for very well comfortable spaces that encourage more walking and social interaction. Each pressurized space is separated with large airlocks that close in the event of emergencies, but they stay open most of the time to allow for the freedom of movement. All of these design decisions teach us that a vast arrangement of buildings are possible. We can create these cities, suburbs, and homes that are as vibrant as any on Earth.
5 minutes until Q&A.
Allowing for natural light, comfortable spaces, and views of the Martian landscape, all the materials used to make these structures are readily available on Mars. We also felt that our farms need to use the natural Martian sunlight, as this is also a massive resource. Ultimately, using electricity to create materials to make farms allows for much greater farming capacity than running lights for covering farm systems. Farms can be simple pressurized environments where crops can grow in the natural sunlight. A basalt fiber reinforced polymer skin will allow for a massive expanse of pressurized farming space that is mostly clear and open to the sky. Using overhead girders as tracks, we can run automated farming robots to do a lot of our farming work. To allow people to work for long periods of time in these farms, we built thick regolith tunnels to help reduce radiation. Automated sails that can pulled over have reflective coatings to trap heat inside the farms at night. These can also serve double duty to reduce dust deposits during the famous Martian dust storms. But these farms don't stand alone from the city. Air exchange with nearby buildings will help clean up the air, stabilize pressures and temperature, and allow people to get their hands into safe, healthy dirt. The water from fish farms on the roof of buildings can also help fertilize farm soils. Together, all these various buildings form a connected city, functionally and socially. We have aimed to design a city for people.
Our mission at Nexus Aurora is giving anyone on Earth a chance to contribute to making humans a multiplanetary species. We would like to thank the Mars Society for creating this great competition to showcase some of the designs and concepts we have come up with as a team. As Elon Musk mentioned yesterday at this convention, one of the most important elements necessary to create a permanent Mars colony is to inspire people so they will have the desire to go to Mars in the first place. This is why Team Nexus Aurora has worked hard to not only present realistic technical and economically viable solutions, but we designed our Mars city-state to be a beautiful and awe-inspiring land of opportunities, where many people will actually want to live. To be one of the 10 finalists out of the 175 international teams is an honor in itself, and any exposure this might gain us will help the cause for Mars colonization. Whatever happens, we are extremely proud to be part of our amazing global team. We invite all the other teams who wish to keep actively working on space colonization, and anyone else interested for that matter, to follow our progress or even become part of our team at Nexus Aurora. Our mission has only just begun, and we need you to make sure we become a spacefaring civilization. As the final part of our presentation, we will now continue to our Q&A, after which we are hosting an Ask Me Anything Q&A on our subreddit, where we will answer the questions anyone might still have.
Thank you. Kyle, your question? Kyle, you can unmute.
Oh, yep. In the beginning, you guys mentioned that you have done some testing with your basalt fibers and pressure vessel. What scale was that on? Because I know as you go larger in radius, the forces become unimaginably large. And what are the sizes of what's necessary to keep your domes from exploding under these pressures, say for the agricultural domes?
So I ran those experiments and they were extremely small scale. So, 20 centimeters tops. The interesting fact though is that you can have, if you have a section that works at 20 centimeters, you can then reinforce it with larger basalt fibers to make it work at a larger scale and then work your way up. Currently, I think for a 10-meter spacing, you need something like on the order of a 10-centimeter thick bundle of solid basalt fiber. It's under tension, so it doesn't actually even need anything else other than the tensile members, but that is an enormous object. And clearly that's gonna be mass that you do not want to lift from Earth.
Thank you.
Okay.
Yeah.
Robert, next, please.
Thank you for that presentation. A number of extremely interesting ideas, and I commend you for even doing some experimental work in support of it. I'd like to, maybe I missed it, but can you discuss your concept of the economic basis of the city-state?
Yes, we have come to the conclusion that other extreme
5
ideas
more minutes for questions.
mentioned by other groups such as cryptocurrency is not actually very viable on a scale of a 1 million city, 1 million population city-state. Our city aims to become, and we have come to the conclusion that tourism will not be a viable source of income because of 9 months travel. And in the 21st century, not a lot of people have time to spend 18 months in space. So what we are trying to become is to become a foundry state of Mars. We are trying to supply the raw resources created by our factories to other nations that want to found other Martian settlement, because we have seen from history of space stations that nations want to have their national things, right? We have Russian Mir, we have the European Columbus program, we have American Freedom Station program, and we have Chinese Chang'e program. We see that nations want to have their national state. And instead of nations trying to deliver the resources required to build the settlements to the Mars directly, we as Nexus Aurora settlement can sell those resources to those nations that want to start their own colony. And we aim to supply other resources to Mars as a basis of reconstruction or maintenance program. And when you go to the next slide, please, you can see that we are trying to get corporate investment into Mars by providing a rather fundamental analytic aspect of quantitative data, because Martian environment is not something achievable in other environments as well. So we believe that Mars have a real corporate moat. Mars have a real advantage over other parts of the solar system. And that is the basis of our economic system.
Okay, George next.
Yeah, so I had similar question to Robert, and I think you answered it correctly. I saw that your exports are 50% industrial materials, and my question was on what planet the customer will be and why Mars would have a competitive advantage as the source of industrial materials for the customer. And your answer was perfectly satisfactory. Thank you very much.
Okay, Samir.
Yes, thank you. I was so much fond and interested in the Garden City concept, but don't you think, I'm just inquiring about having, is it realistically to have this kind of huge large gardens or parks on the surface being bombarded day and night with the alpha beta gamma rays from the cosmic rays from the solar flares, in addition to the blockage of the sun due to the dust storms? And actually in the sunny days also it's about 40 to 60% maximum of the radiation like on Earth. So we have like too many challenges regarding having big large gardens on the surface. So how did you think about figuring this out?
So in terms of the farms, so we've got gardens, but the farms are actually connected to the city. So when we talk about gardens, that they're very much a connected relationship between the farm and people. But we'd also have gardens inside the habitats themselves. They should have enough light there under the water for where there would be a safe radiation protection. We've looked at quite a bit of research in terms of what radiation does to plants. And it seems that after germination, there seems to be very little negative effect for one season of growing for plants on Mars. And the tests that people have done on plants that grow is much, much higher than anything that Mars will see. So we found that plants should grow fine on the surface of Mars. You don't want people to spend too much time on these unprotected areas, but under short stay periods, it should be fine. And people should spend most of the time under the buildings with water radiation protection overhead.
Okay, Frank, we have time for a quick one.
Okay, I'm wondering how such a geographically diverse team got formed. Who was the key element in this?
I did that one. We just came together over the internet. We were in lockdown and we were bored, so we decided to build a Martian city. It seemed like a fun thing to do, and that's where we are now. So we're very, very we're incredibly proud to have gotten this far with a team of, in effect, amateurs who came together literally 6 months ago to do this as a community. It's an amazing thing to have done, and we're honored to be here today.
Time is up.
Encourage you to continue, and it sounds like you are. So I'm happy to see that.
Thank you. And we're continuing the Q&A as well on our subreddit. The link is there. So please do click through if you want to ask more questions. We can provide the answers.
Thank you very much.
Thank you very much. A lot of really great presentations, a lot of very original ideas. Thanks a lot.